recreate that mineral assemblage, those mineral compositions in the laboratory. And this is my former PhD student, Duncan Muir. And these are the stability curves of different minerals. This is temperature and pressure. We're aiming to have orthopyroxene and biotite, and that's that little skinny volume there, which again is giving us a pressure of about 100 megapascals, although there's some slop in that value. So what the daysites tell us is that these magmas will last stored, they last equilibrated at shallow level beneath the volcano. So geophysics says there's something very, very deep. The petrology tells us that the magmas, at least just before eruption, were stored at shallow level. The picture that emerges here is that this system at shallow level was formed by repeated incursions of dacite magmas into a shallow reservoir. There are heating and cooling cycles. Those are recorded in the temperatures of eruption, but also in the breakdown of some minerals. The dacite is rather water poor, and that may be significant in terms of the explosivity of this volcano. Volatile saturation is at about 100 MPa, and I've mentioned before these hydrous andesites that form these little mafic enclaves or mafic inclusions. The striking thing about those is they have really, really calcic plagioclase, anorthite 85% mole percent of the anorthite component. We have an image then of the magmatic system, and this is from a paper of Duncan's. This is the shallow storage region where the magma is last equilibrated. This is the APMB, that geophysically anomalous deep body, and we infer that magmas that erupted or were generated here ascended, equilibrated briefly before eruption up here, and then emerged onto the surface. So we are invoking a connection between the shallow system and the APMB. This is the distribution of earthquakes today. Actually, we don't know the distribution of earthquakes 250,000 years ago. What's in the APMB? Well, this plot on the right shows two different ways of working out what's in the APMB. The first way, which is the top plot here, is to say the conductivity of the APMB as measured by magnetotelluric surveys is 1 Siemens meter, and we've then made, this is made measurements of the electrical conductivity of andesites with different amounts of water, andesites similar in composition to these little mafic inclusions, to see how much of that andesite we would need, what its water content would be to match the conductivity of the APMB. And in fact we find that we need a melt fraction of about 10% and a water content of about 9%. So we need a very, very wet andesite to match the electrical conductivity. And I should say that we can't do it with any other melts. They're less conductive, we need an awful lot more, and that doesn't really fit with the seismic wave velocities. There's another way we can assess what's in that APMB. I've mentioned we have these little blobs of andesite, and they have a very distinctive mineral assemblage, including very, very calcic plagioclase. And in the laboratory, we've tried to reproduce that very calcic plagioclase, and in fact the rest of the mineral assemblage. And we find here are the experiments, the green symbols. To get 85, we need 9% water. So we actually agree that what resides in this deep crustal system is an andesitic melt with 9 weight% water. And that has a lot of implications for the amount of volatiles that will be discharged as this body evolves. And just to give you an idea, the total amount of water dissolved in the melt in the altiplano magma body is equivalent to Lake Superior. So it's an entire underground, mid-crustal Great Lake. I'm not going to dwell on this slide, other than to say that it's not just andesite down there. The andesite is at 980 degrees, it contains a lot of water, and it actually melts the crust above it. And we know it melts the crust above it, so imagine, that's the one. It's hot here, this is the older crust, this depth is more like 15 kilometres. There's melting that takes place of the crust here, and we know that that's taking place because if we look at the strontium isotopes, we have dacites, these are the Uruku magmas here, we have dacites, but they're very, very radiogenic in terms of their strontium. So that tells us that this region is a place not only where magmas are crystallizing, but where they're also melting the crust. So we are fueling this region with basalt from the mantle that differentiates to produce very hydrous andesites that supply heat and melt the crust. And here are just some thermal models from the old paper of Annen. I won't go into the details, but the point is that in the deep crust, because you're putting heat into a relatively insulated environment, you differentiate by crystallization, also by melting the crust. Okay, there's the, here are various geophysical images. Let's not go through the details, but the point is, I think this is probably the best geophysically imaged deep crustal magmatic system anywhere in the world. We have, this is ambient noise tomography, this is magnetotellurics, this is geodesy, there's a big region of uplift and the surrounding region of subsidence around Uruku. We've done a gravity survey, these are low density bodies, that's Uruku here, and all of them show some sort of a connection from deep up to Uruku. It's less clear, there's less resolution in the ambient noise tomography. The gravity, obviously a rather non-unique technique, but we can see low density fingers extending from a depth of about 15 kilometres up under the volcano. We're getting images of this system, the system that connects the APMB to the shallow level and ultimately to the volcano itself. And there are a number of interesting things we can do with that configuration. If we go back to the geological map, we see that the youngest magmas, shown in the pale colour, are close to the summit of the volcano, and they're all rather short flows. And the older lavas are around the periphery of the volcano, and they're much longer flows. They come from the same vector, but they flow further. The other thing we notice is that this is Uruku, this is Sonikera, this is the Altiplano. These are just two dormant volcanoes. These are the volcanoes of the Altiplano. There's Uruku, Sonikera would be there. These are a bunch of others. Just take these off Google Maps. They have an average height of 1.3 plus or minus 0.4 kilometres above the Altiplano. Some of them have been decapitated by erosion. Uruku's a little bit damaged at the top. By and large, all these volcanoes are the same height. And that's rather interesting if we think about a very simple system where we have buoyant magma deep in the crust, and we have denser crust lying above the buoyant magma. We would expect in a system where there is a connection that there'll be some relationship between the depth, the composition and the density of the magma and the height of the volcano. So we might imagine that the height of the volcano is controlled by that depth and by what's in the magma chamber. It's obviously a very simple relationship. We're in a fortunate position because we don't have to speculate about the water content and the temperature and the composition. We have a complete set of experiments that we can use to turn magma composition and crystal content into density. We can actually calculate the density all the way up. We have a less good constraint on the density of the crust. This is a regionally average density variation in depth. And so we can actually, rather than use this very crude method, we can actually integrate the density difference all the way across the crustal length. And we can calculate the height of the volcano and different ways produce different answers, but they're always about 1.6 kilometres. So what we think is that this volcano continues to grow to a height that matches that density contrast beneath what's at the top of the APMB and the crust around. And what that opens up is the possibility that if we disturb Uturunku, if we, for example, destroy the edifice, it will over time try to reconstruct that edifice. And it leads to an idea of top-down volcanism, where actually the magmatic system may be controlled by what happens at the surface. And one interesting possibility is that this change in output rate here, around about 600,000 years ago, might correspond to particularly intense glaciations in the region. You can sort of see this is the oxygen isotope curve. I won't go into details for why we can see a change in the intensity of glaciations around about 600,000 or 700,000 years ago. But one possibility is that this is a response to partial destruction of the edifice and then the renewed growth. Okay, let's now move to a different volcanic system to try and understand what does all this look like, or what does a transcrustal magmatic mush actually look like if we got our hands on a piece. I've just shown you geophysical imaging. Well, the best place to go for samples of transcrustal magmatic mushes is the Lesser Antilles. Lesser Antilles is a chain of volcanoes. This is in the Western Atlantic, is South America. This would be Florida up here, North America. And there's a chain of volcanoes that correspond to westwards subduction of the Atlantic beneath the Caribbean plate. And these volcanoes are well known for their crustal zeniths, plutonic zeniths. And I've now been to every single one of those islands. It's been very hard work. But we've collected more than 1,000 crustal zeniths from all along the arc. Some of them, as you can see here, are really, really very large. Many are rather small. It's the biggest collection of crustal plutonic zeniths of any volcanic arc in the world. And I'm very keen to share that collection and to collaborate with anyone who's interested. The key thing about these samples is they are very, very rich. All that blackening on there is amphibole. The volcanic rocks of the Lesser Antilles never contain any amphibole at all, with a few exceptions. And yet the samples of mush, partially molten rock, are abundant in amphibole. These are rather nice. This is a QuemScan image from a former master's student of mine. And we can see pale blue plagioclase, yellow olivine, green pyroxene, so that's a troctolite or a gabbro, and then this browny red colour here is hornblende, and we see the way in which hornblende imprints itself on top of an original anhydrous mineralogy. And I'll show you just 4 more samples here. In each case, we can see these big plates of hornblende. These are the plagioclases, olivines, and pyroxenes. This is from St. Kitts. This one's from Beckway. We can see rather interstitial amphibole here filling the gaps between the crystals. This is also from Beckway. We can see these huge poikilocrysts of amphibole that are overprinted on an earlier anhydrous mineral assemblage. And then here is Grenada. That's a rather idioticized olivine and pyroxenes and plagioclase. One of the things about transcrustal magmatic mushes is we would expect them not to be static, but expect melts to percolate up through the crystalline framework, modifying the mineralogy as they go. And those melts, as I've shown, are very, very water-rich in the case of the Andes, and the products of that reaction is amphibole. So anhydrous minerals plus hydrous melts will give us amphibole. What pressure is all that happening at? Well, I have a postdoc, Lucas Hiberna, who is developing barometers. The way these barometers work, this is not an empirical barometer. What we're actually doing is we're taking the internally consistent thermodynamic data set, that you probably know known as Thermocal, from Holland and Powell. We have a series of reactions. We select appropriate reactions for the mineral assemblages we see, and then we look for the intersection of those reactions in PT space. Now, what we've done is, rather than use all of the thermodynamic parameters from the Holland and Powell dataset, which are optimized for all of the composition space. We've focused on just those minerals that we get in these assemblages. And what we've done is we've recalibrated Holland and Powell for the specific set of reactions and mineral assemblages that occur in the Lesser Antilles cumulates. And I won't go through this slide in detail, but what we've done is we've taken all of the experimental literature where we have these mineral assemblages, in this particular case, assemblages that contain olivine, clinopyroxene, and plagioclase, or olivine, clinopyroxene, plagioclase, and spinel. And these are all the experiments out there. We've made quite a lot of experiments of our own. We've recalibrated and we've refined the activity composition relationships. We won't go into details on this. I just want you to be reassured that this is not an empirical approach. We're trying to actually develop a robust thermodynamic approach. Here's one example from Grenada. What we've done is we've found patches of this rock where olivine, clinopyroxene, and spinel are in contact. There's a lot of amphibole in here, but we've found little islands where that's olivine, clinopyroxene, and plagioclase, olivine, spinel, clinopyroxene, and plagioclase. We found places where they coexist, and we calculate the average pressure from two different barometers. We're getting around about 3 kilobars, and one of Luca, the postdoc's tasks, is to calculate the pressure for all 1,000 cumulus analytes and to get an image of what the crust looks like beneath the Antilles. And one of the problems here is we don't actually have a really good thermometer, which is why I was very interested in Alex Sobolev's thermometer between olivine and spinel, because that would give us an independent constraint on the temperature. Okay, so we've got geophysical images of a mush. We've got petrological samples of a mush, and they are from around the right depths, 7 to 14 or 2 to 4 kilobars. I haven't determined all the pressures yet, but we're looking at sort of mid-crustal depths, much thinner crust in the Antilles, of course. Now let's focus on that process of getting from the mush to the volcano, that connection. And I'll now turn to a third field example, which is Mount St. Helens, a volcano in the western United States above the Cascades, volcanic arc, subduction zone. There's Mount St. Helens. The Nazca plate, sorry, the Blundy Jon plate is subducting like so, and St. Helens and Mount Adams are roughly along a line perpendicular to the trench, and this is again a magnetotelluric study. This is showing resistivity now, so low resistivity here is some sort of deep melt layer. There's currently a big project to refine that. This square should move over here, sorry. But we've got a deep transcrustal magmatic mush that appears to be linked to St. Helens and Mount Adams by one or more of these columns. This is a close-up of that region there, and this is an older image where we can see the distribution of earthquakes appears to define earthquake-core regions that are often thought to represent magma storage regions, or little magma chambers, if you like, little regions where the melt functions. So let's see if we can learn something about the process of moving melt from here to erupt at Mount St. Helens. So we're just going to look at the centre melt from the deep crustal reservoir to the volcano. Later I will also point out this is undoubtedly when melt comes, we can see that very clearly, but also gas will come out. Magmatic fluids will come out. So, to get some insights into the ascent process, we're going to look at textures, the testimony of textures. These are plagioclases. The different greys are different amounts of the amorphite and albite component. These are beautifully zoned plagioclases, and I always think that zoned minerals like this are like mute witnesses to some event. They're trying to tell us what went on before they erupted. They just don't know how to tell us. We have to work out how to ask them the right questions. There's an awful lot of information locked in these zoned crystals. And I'm just going to focus on the more normal zoned crystals like this rather than the real weirdos like that. So wouldn't it be wonderful if we could interrogate an individual crystal and get it to reveal its life story, if you like, if we could ask the right kinds of questions? Mountain Helens is a really good place to do this. Firstly, it's a very, very well-studied volcano. We have very good constraints on the phase relations, the relationship between temperature and pressure in terms of mineral stability. There are a lot more data than this. I've had several PhD students refining these phase diagrams. We've got very good constraints on mineral composition. So, for example, in terms of plagioclase, we can parameterize the composition of the plagioclase as a function of temperature and as a function of pressure. These are different pressures here. We see a variation between both temperature and pressure. And best of all, Mountain Helens, a bit like Utarumpu, is a very, very monotonous volcano. There are some slightly more exotic rocks, particularly cumulate xenoliths at Mountain Helens, but over its last eruptive period, it pretty much just produces dacite. So we can tend to view it as a relatively closed system, and that's really rather important. Okay, so in principle then, we could just take a parameterization of plagioclase composition in pressure temperature space. These are lines of an orthite 30, 35 and so on. That's the liquidus and that's the solidus. And we can say, right, we've got a zoned crystal. How do we move across PT space? Well, you can see straight away there's an ambiguity. Let's imagine that was our zoning. Well, we can achieve that zoning by going that way, dropping the pressure, or we can achieve our zoning by going that way, dropping the temperature. So the path is not uniquely defined. Let's imagine now that we can add another variable. You'd say, well, there's a difference in the water content between here and here, but not a difference in the water content between here and here. What if we could get the water content of the coexisting melt? Well, here are contours of water content, and then we might be able to do something a bit more with the zoning. We could say this is a drop in water content, whereas this has the same water content. We can, in principle, measure the water in a plagioclase, and we can use that to determine the magmatic water. That's not very straightforward, and there are some issues with the relatively rapid diffusion of water, so I haven't been able to do that. Let's try something else, though. Let's look at melt fraction. Let's contour that same plot for the melt fraction. These are lines of constant melt fraction, 100%, 80%, 60%, 40%, and so on. The lines of melt fraction or crystallinity are oblique to the plagioclase composition. So there's a difference then in going this way and that way in terms of how the melt fraction changes. So, if I had some means to use the plagioclase to determine the melt fraction change from one zone to the next, I would be able to distinguish between the case where the pressure drops and the case where the temperature drops. The way to get a handle on how the melt fraction changes is to measure partition coefficients, to measure trace elements where we know the partition coefficient. So what we've done is we've started the program of analysing trace elements and anorthite across zoned plagioclase crystals. We're going to make the assumption that the system is closed, and we're going to navigate our way through pressure, temperature, melt fraction space. So, we make measurements with iron probe from the rim to the core. We look at the zoning in anorthite, strontium, and barium. We assume the system is chemically closed on the scale of an individual eruption. We assume that growth occurs at equilibrium. I'm happy to address questions on that if anyone's concerned. We'll assume that there is no diffusive re-equilibration. We'll actually demonstrate that quite convincingly in the case of strontium. These crystals, as you can see, can't be very old. There's been very little diffusive re-equilibration. We know the partitioning of strontium and barium between plagioclase and melt as a function of composition and temperature. That's from a paper that I'm drafted over. I've got a parameterization of plagioclase composition from all those many, many experiments, and melt fraction. My chemically closed system is going to have the composition of the bulk magma erupted in 1980 to 86. I'm going to use plagioclase melt thermometry to get the temperature as the starting point. And then what this is actually a collaboration with Oleg Melnik. What Oleg does, actually do, is they then uncrystallize this crystal. They start at the end and they work out what amount of crystallization must have occurred to get from that point to that point, and then that point to that point. So they progressively uncrystallize the crystal. They maintain mass balance in the system at each increment. They recover the pressure, the temperature, the melt fraction, the proportion of the crystals that are plagioclase, and the composition of the melt in terms of strontium bearing. As well as having all those experiments, I've also analysed just over 700 melt inclusions from Mount St Helens for their water contents and trace elements. So we have a very good handle on how melt varies in this system, and the solutions here are optimised to melt, to match the melt inclusion strontium bearing. Okay, let's see what this is. That's a lot of talking. Does it actually work? So here's one crystal from the 18th of May 1980. This is the rim and it's a core. This is the anorthite content. It wiggles around a bit. Here are two profiles that goes that's that, that's that. Then we measure the strontium, blue, and the barium. And then using Oleg's method, we recover the pressure on this scale. Big pressure drop just there, and then a lower pressure. And the temperature in red, there's a drop, and then it rises, and so this drop in pressure corresponds to a rise in temperature. This here is the amount of crystal, the amount of melt fraction, I should expect. The magma is crystallizing, the melt fraction goes down, that's this axis here, and this is the proportion of plagioclase which starts out quite low and then becomes the dominant crystal. So we can do that for many crystals, and we can work out what that's telling us about the magma ascent process. But we need to key that into some other information, otherwise this is just idle speculation. Well, I mentioned that I analysed a lot of melt inclusions, and this is some published work. I don't have all the melting, I find it later find it. That's yesterday. These are the water content of melt inclusions from Mount St Helens. This is their silica content, and as silica goes up, that's crystallization. Water goes down. This is a process of decompression crystallization. We also took individual melt inclusions. You can see there's a little plagioclase in there. We were able to analyse the plagioclase in the melt and do plagioclase melt thermometry. So for a subset of these inclusions, we were able to measure water and temperature. We know the solubility of water as a function of pressure. So we get a pressure-temperature path that shows, as the pressure goes down, the temperature goes up. And the reason for that, of course, is these are magmas that are driven to crystallize because of decompression. The crystallization releases latent heat. The latent heat causes the temperature to rise. And this amount of heating is entirely consistent with the amount of crystallization we see. Very lowest levels, it's driven by microlite crystallization. So, this is one record from melt inclusions. I've just described a method from plagioclase crystals. Wouldn't it be great if they agreed? I should have done this some while ago, but I was talking to Oleg about this yesterday. I said, I'm a bit worried, Oleg, that these two records don't agree. So last night I thought, well, I'll find the date, I'll plot them up. It would be embarrassing if they didn't. But if they didn't, I wouldn't plot, I wouldn't have shown them, obviously. And they agree pretty well, actually. These are four crystals, cores to rims, pressure and temperature. This is the journey that plagioclase is testifying to in terms of pressure and temperature. This is the journey that plagioclase testifies to from core to rim in terms of pressure and melt fraction. This is the story from the melt inclusions. You'll recognise that curve from the last plot. This is how the melt fraction varies, crystallization this way. They're in remarkably good agreement. And it makes me quite confident that plagioclase and melt are reliable witnesses. They both saw the same event, but they saw different parts of the event. The plagioclase is recording something much deeper than the melt inclusions. The melt inclusions record this 200 MPa up to the surface. Plagioclase tells us about deeper in the system. And these pressures here are where we think the mid-crustal reservoir might be. So let's make one more check. Let's see whether the story from the crystals is commensurate with the geophysics. Let's try and complete the circle. So in the top left-hand panel there are all of the pressure points from all of the zones of all of the crystals we've looked at, turned into depth using that density. I could have changed the density, but we'll stick with this one. So it says a lot of the crystal zones were grown at shallow depth, and there are more up to about 16 kilometres. Let's look at the earthquake distribution over the last 30 years beneath Mount St Helens. There's a lot of this scale is the same as that. That offset is because these are reference to sea level and this is reference to ground level. So there's a 2 kilometre offset. The earthquakes have a large peak here, shallow, and they range down to about 20 kilometres. Plagioclase goes down to 16. So the seismology and the petrology are agreeing on where magma is. And this is a very large project. I'm not part of this, but this runs out of University of Washington. And they're imaging the magmatic system. There's Mount St Helens. That says shallow magma storage zone, and this says deep magma storage zone. There's a passage between the two. This is reference to sea level again, so that's 7 or 8 kilometres, and that's the surface. I think we're starting to get petrology and geophysics reconciled. I think that's a really exciting development. Rather than speaking a different language, we're starting to agree. So the final thing I'd like to talk about, that's okay. Or should I talk at the beginning of your... What I'll do is I'll just describe this, and then this part of the talk relates to hydrothermal ore deposits. It segues into what Oleg will be talking about after the break. And so I'll just introduce it here, and then I'll stop the talk. Here's how we think these systems work. We think we have a transcrustal magmatic mush that comprises a series of melt-rich lenses, crystal-rich lenses, and gas-rich lenses. And these accumulate over time and are inherently gravitationally unstable because we've got low-density melt and the high-density crystals. We've got low-density gas trapped in little lenses. We think that in this system, gas, melt, and crystals can move in a decoupled way, and that periodically the system experiences perhaps quite catastrophic overturn. Something I didn't say about the crystals at Mount St Helens is those rims, that journey has to have taken less than 3 years. It's based on the diffusion trace elements. We think that the fluxes of gas, melt, and crystals out of this volcano are decoupled. They move independently of each other. And here's a lovely example from Soufriere Hills. This is the volcano when this photograph was taken. These little bright spots are fumaroles. They've been there pretty much for the last 10 years or so. They release gas, but the times of gas release are often completely, or typically, completely decoupled from the times of magma release. So this plot at the bottom here, when we see red, the volcano is erupting, green, it's dormant. Down at the bottom here is the gas flux. This is a dormant period. There's lots of gas coming out, but there's no magma. Here's another dormant period. Gas comes out, quite high, but there's no magma. Sometimes they're coupled, sometimes they're decoupled. And I think that has implications for the way in which hydrothermal ore deposits form. But that's something I'll come on to just before Oleg's talk. So I think the final slide should be... No, I'll stop. Thank you.
Вам объяснил, что очень раньше,
That's right.
What's your explanation of that?
Good question. The reason is, I think, let's see if I can find that slide. The reason is this, that the proportion of plagioclase crystallizing early on, deep, is really quite low. So a relatively small number of plagioclases crystallize deep, and rarely do we have melt inclusions right in the cores of the crystals. So the melt inclusions tend to occur in these sieve zones around the outside of the crystals. So cores tend to be a small proportion of the crystallizing assemblage, so that reduces the chance of getting an inclusion. But inclusions are very rarely, you can see here, you very rarely have inclusions in here. Inclusions arise in this crystal. They tend to occur just there, and then around here. This rapid decompression here seems to correlate with burst of melt inclusion traffic. So I just don't think we have any.
I would suggest another.
Yeah.
Maybe 2.5 kilobar is an upper level of pressure which can hold inclusion in such weak metal like that.
Well, that's actually a certain possibility. There's one thing I'd say about that. We do have a small number of melt inclusions. I found 5 that have really high carbon dioxide content. Now, one could argue that those are artifacts. I've reanalyzed them. They have high CO2 content. They suggest pressures of more than 4 or 5 kilowatts. I'm not absolutely confident that I trust those melt inclusions. So you may be right. Plagioclase may be a rather poor container. I have looked at pyroxenes, and I don't find any deep melt inclusions. Amphiboles nearly have always leaked. There are no olivines. So it's a good point. Either melts weren't getting trapped, or even if they were trapped, they just don't survive.
Maybe both.
Or maybe both, yeah.
Yes, John,
Yeah.
you showed nice crystals of amphibole with numerous inclusions.
Yeah.
And interpreted like percolation of the melt. Can you explain the physical state of the host rock? What was the temperature approximately? Why there are no beams which...
Yeah, that's a very good question. So you're referring to those images? I don't know is the answer. So a very simplistic answer would be to say I have an interlocking network of crystals. I have some interstitial melt. This melt is moving out. A new one is moving in. It's reacting. It's producing amphibole, and then it leaves.
It might be the metasomatic process.
Oh, it is a metasomatic, absolutely. One of the things I should say, and this is a sort of a paradox that has emerged in recent years, is if you look at many volcanic islets, their geochemistry says amphibole fractionation. And yet you look at their phenocryst contents, they're on the amphibole. And the Antilles is a really good example. So I suspect that all of the melts that eventually leave at the top of this crustal column have somehow experienced some modification by these percolative processes and have precipitated amphibole on the way, even though they no longer saturate with amphibole on eruption. There are lots of questions like the one you've just asked that I think are relevant here. What is the actual, this is a percolative reactive flow. What happens to trace elements as you move through here? What's the stoichiometry of the reaction? Is it dissolution, reprecipitation? We see some really weird stuff in the trace elements in these rocks, but as a whole, I don't really understand those. I think this is a metasomatic percolative process, a bit like you get in a metamorphic rock, as you pass a fluid through a porous medium.
Jon, I was surprised very much when you told that geophysical data showed that practically there are no liquid magma chamber for only mesh, or mesh, how we pronounce it. And for instance, in polar Siberia, hundreds of dikes. And these dikes consist of olivine crystals and ground mass, just quenched ground mass.
Yeah.
So it means, but we can propose that other crystals dropped or some disappear. Yeah, but olivine here, so the most dense phase.
Yeah.
So it means that must be big amount of melt. Yes.
Okay.
So,
I see what you're saying. I think we're talking at cross purposes. What I envisage here is this region here has pockets of, the average melt content is, let's say, 20%. In places, the melt is 100%, and in places it's 0. The average, the geophysicists are just telling us about the average, across the average to melt. I would anticipate that in here, there are some lenses. Imagine building this from a series of sills. The sill that arrived last week is 100% liquid.
yes.
Now, if that can find a way to the surface, if a crack can propagate, it can travel up, crystallising very little on the way, and it looks like a dike with sparse finger crisps.
Yes.
Another part of the system, say here, was injected, it solidified, it got reheated, cool. It spends nearly all of its lifetime, maybe several million years, in a near solid state. And I think the important thing is that if we were to zoom in at any point into one of these mush zones, we could access a region that was very, very liquid, or very, very solid, or somewhere in between.
Yeah.
So I think what you say is not inconsistent with this. What I was saying about geophysics is that if we want to find bodies of magma that are equivalent to the size of erupted volumes of big caldera-forming volcanoes, there aren't any. The volumes of the crust that can be entirely liquid are really small. I think they're just little lenses within this mush.
Maybe in ancient time, commodity, definitely liquid, but they of course old.
Yeah, I don't want to speculate about the Archean.
Yeah.
I'm sticking to the modern. Yes.
Modern mathematics. Yes. Thank you.
Okay.
More questions? Okay. Thank you very much.
Thank you very much.